I have to use this? Probably not. Well, let's see how far we can go without microphone. So, as you probably recall from the last talk, I suggested that I provide some information on how to actually conduct these factorial studies. Most of the most important aspect of this methodology is to provide appropriate research design. So then, for that reason, I'll talk about two types of designs. One that involves AND and OR decision gates. And we call this disjunctive rules physical structures. I'll do a couple of examples. And after that, we talk about the novel signatures of a holistic or configurable perception. And that answer that you can recognize somewhere here. Again, just remind you about general definition, general approach to a ballistic hypothesis. We say that objects are perceived as whole entities and not a simple sum of features. And we use kind of, at this point, maybe interchangeably with a configurable perception. And the second one would be pitted against the analytic or feature-based hypothesis that the perception of object occurs at the level of a feature. So one way to learn about underlying processes is to learn how they are organized. What is their processing order, what is the stopping rule, what is dependency between processes. We listed those as fundamental processes of fundamental cognitive properties of elementary processes. And one way to learn about these processes is to apply system factorial technology. And as I said, there's a bit of history of application, of development of the approach, and then there's another, I would say, last 10 years we see pretty much explosion, if I may say, of the application of such methods in a different area. Here's a SFT design in a nutshell. That's from my recently accepted paper in Frontiers. Editor here is Cheng Ta. You know how Frontiers papers are very tough, to publish. You only have to provide enough money. But actually, there's a peer review process, and I just show you one excerpt from this paper. It's about SFT approach and what it makes. What is it actually? How do we use it? So let's say that you would like to learn about an n number of processes. So you believe that underlying structure, let's say we have n number of processes, just need to identify them. Then your design, because now it's all about experiment, the design should have n independent variables. And this is the first requirement. Let's say think about maybe two processes that you would like to learn. One could be configurable process of eye separation. The other could be second order relational feature, such as nose and lips difference. Two features, configurable features, and we would like to learn how they're processed, how this information from processing these two features are combined together. Are they serial or parallel? Do we use stopping rule? What kind of stopping rules? Terminated, exhaustive? Are these two processes independent or not? So you need to have in the design two independent variables. So this is the first thing, at least two. So I'm talking about here a condition that requires at least a requirement. So now we have two independent variables, two processes, three processes, three independent variables. Now, second manipulation, very important manipulation, is to add saliency to this whole process, to the whole method. The saliency is operationally defined here as a manipulation. So there's a certain experimental manipulation that selectively influences a single process of interest. Yes? Such that the process will be speed up, and we call this H, high saliency, or slow down, in which case it's low saliency. Right, so this is the second requirement. We have two variables at least, and we have to manipulate saliency of these processes. That means, again, if we have second order relational features like eye separation, we have to find eye separation that makes high saliency case and eye separation that makes low saliency case, at least. Right? Now if you combine the two, you have to combine them in a factorial fashion. So you have first order relational, second order relational features is eye separation that is on the manipulated level of low and high saliency, and you have the other feature, let's say nose position, nose to mouth difference, that is also manipulated at a low and high level. So this is factorial manipulation. That's why the name is system factorial technology. The total count now is 2 to the n. The total number of experimental conditions at least you should have in your design to learn about the fundamental properties is 2 on the power of n. Here n is number of processes, right? 2 comes from these 2 levels of salience. So if you would like to if you would like to learn about 2 processes, you need 4 conditions. If you would like to learn about 3 processes, you need 2 to the 3, which is 8 conditions. And so on and so forth. You see, if you increase the number of processes, our aspiration goes up, and the number of conditions really exponentially goes up. All right. So that is as simple as this. You have to follow these guidelines, and that's how you can arrive at a system factorial technology method. Again, what do we learn? Here's what we learn about different mental architectures. We learn serial terminating, we learn serial exhaustive, parallel terminating, parallel exhaustive, coactive. I mean, possible catalog of this mental architecture, maybe we can add more here. Maybe special architectures could be involved. We don't know that. But, if you envision that you might be willing to investigate certain type of architecture, you may be able to find it. I doubt, that I don't doubt, we can include it here and then maybe find specific signature for that architecture. So this is how they are presented, again. Let's say these are 2 features, second order relational features, eyes and lips all the time, but we see that here in serial order, and they can terminate here on eyes. You don't have to process lips, and that's OR gate. Yeah, this is called OR gate. Here we have serial exhaustive. You process both features, it arrives at end gate. So you sequentially process one feature, then don't make a decision, turn to next feature, analyze it, and then proceed to the end gate and then make a decision. Is that the phase that I know, or is that another phase? And so on and so forth. We have parallel system, parallel, so we process them in parallel, but the first one finishes, it's parallel terminating, or parallel first terminating process, as we used to define it here, and parallel exhaustive, which we have to wait for both of them, but in parallel occurs processing. Yeah. And this is the coactive. We glue together information of an identification of separate features into one unit. So instead of eyes and lips, maybe we have a combination of eyes and lips. Maybe someone's Joe's or Bob's, eyes and lips here. Like a grandmother cell, maybe exemplar, stuff like that. And then it feeds into the decision unit. All right, so these different architectures, we see that last time we given different labels because we started to think, okay, holistic analytic, have different properties when we break down to this serial parallel stopping rule and dependencies. Yeah, this one, coactive, we believe it belongs to strongly holistic processing, because instead of dealing with the isolated features, we're dealing with the combined features. So on the right-hand side, these are different signatures revealed by system factorial technology. These are called driver interaction conscious function. Here this function is flat. So see at the moment this is a signature. Yeah? So indicator. So if the outcome is a flat, then this is the underlying architecture. If the outcome is negative and positive with equal areas, then this is a serial exhaustive. If you have a positive function all the time, this is the parallel self-terminating. If it is negative all the time, parallel exhaustive, and coactive has this negativity, but overall in a larger positivity expressed here. So different signatures of SAC. So that is very indicative. You can see how different signatures will indicate different underlying mental architecture. So that's how we identify them. In a matter of fact, for the SFT, as I said, it's non-parametric approach in the SS. It could be parametric, but in this version, it's non-parametric, so you don't have to fit the results. if you use the guidelines from the previous graph, make a design, accumulate data and calculate these signatures, then you would say, without any model fitting, you would say, oh, this is what is going on underneath. Yeah, so, in a matter of fact, within the SFT approach, there are two signatures used, and one is called mean interaction contrast. Here, we didn't talk much about this one. It is also based on the double differences of, in this time, reaction times for these experimental conditions. They're pretty much in a low, 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 high, high, low. They correspond to different level of salience. If you remember that one, we have to have a low and high saliency of our factors. And then this is the first, and the second one indicates, in this particular case, could indicate maybe facial feature. Is it first facial feature or the second facial feature? First process, second process. In this case, both processes are low saliency. In this case, the first one was low, and the second one is a high saliency. And what we find is mean interaction contrast, which is it is pretty much identical to what we use, to test ANOVA interaction test significance. To learn about the cognitive structures, the factorial technology uses this kind of full factorial design. And if you have two factors with two levels, we find this interaction contrast, and it tells you something about properties of processes. So these are different signatures used. Now, we didn't talk much about it, but the point is, the mean interaction contrast is also associated here. We have this mean interaction contrast is additive. If you remember additivity from ANOVA, here it's under additive, here is over additive. This mean interaction value is larger than 0, smaller than 0, here is equal to 0. It can be used also to predict or to indicate the presence of different mental architectures, zero parallel, coactive, or stopping rule. That's another way, another signature maybe to investigate. Now, unfortunately, this one is not as good as the next one that we mainly discussed. This is about interaction contrast, in which instead of now means, here we have functions. So each of these conditions corresponds to one particular experimental condition. Remember that we have, in this particular case, we have two processes, two levels of saliency. That means 4 conditions. Let me count. 1, 2, 3, 4. Yeah, here they are, right? We find double difference, and because these are 4 functions, the outcome would be another function. This is a signature that we talked about. There's a mathematical correspondence between MICs and SACs. As a matter of fact, if you calculate integral of that expression here, integral of Savannah function will result in a mean value for the particular condition. So calculate integral of that function, the area under the curve, here we get the MIC value and these means. Yeah, so this is a correspondence. SAC provides better insights because it has better diagnostic properties than MIC. Because it's function, it provides more information than MIC, which is just comparing 4 dots. Now let me show you actually how do we do that in simple terms. So let's say that underlying architecture that you would like to learn consists of 2 processes, but we don't know whether this is a serial or exhaustive organization like this. So I just put it as an example. So let's say we have 2 processes and you find 2 manipulations that can affect only these 2 processes. This is called selective influence. So your control would be to manipulate process A with some experimental manipulation, and such that that manipulation will speed down and slow down or speed up that process of interest only. So this one will manipulate only A and not B. So maybe that could be removing the eyes from each other. Then you have to do the same thing for the second process of interest. So on another manipulation, it will affect only B but not A. This is our hope, good. And then most of our experimental methods rely on this idea of a selective influence. This is a critical assumption in experimental psychology. So you find this manipulation, you propose 2 processes there. So what you have to do is you just have to combine these manipulations in factorial fashion. We have low, yes, in the case where both processes manipulated are somehow that they're slowed down. So maybe, for example, you put some mask over the eyes here, and mask, this is mask over the ice, and if it is fast, you remove the mask. So that makes this fast slow. And maybe this is a mask over the nose, lips area. So when the mask is present, you have slow. When the mask is absent, you have fast processing. And that's, probably likely a good way to maybe deal with this whole design. So you can design, when both masks are present, we have slow condition. You see, like this is one condition in experiment. And that's, factorially combining, orthogonally combine these levels. We got fast, slow, fast, and fast, fast. So your experiment at this state, at this moment, has 4 conditions. That could be, for example, designed like this. So you have 2-dimensional space. So you have eye separation and ellipse position here. So you can eye separation. You have 2 groups of faces. They call these jets. I mean, these guys are called sharks. As you can see, if you go along that dimension, eyes are more separated. So jets and sharks. If you go to this dimension, ellipse position, we see that lips are getting closer to nose. And let's say that as experimenter, you set up, this decision criteria, or somehow you impose this criteria by saying, well, look, these are the gang members and these are the other gang members, and then you are presented with one face at a time. You have to decide whether you're seeing sharks or jets. So press shark, if sharks, press left button. If jets, press right button. So how do we get, these factorial manipulations that we discuss here, as you can recognize HH, low, high, low, and low, low here. Now, saliency of these features is defined here by the proximity of that feature, to the, in these faces of that group, to the proximity to the other group members, the opposite group members. So the fact, that this distance between eyes is close to the opponent group member, you have to give a different response, make processing of that particular feature slower than that of that guy here. So this is a low level, and this is a high level. And see on the first feature, on the first dimension, high, low, we had change. And the same thing across the other dimension. Do you see that now? This is one way to do it. The other maybe would be using masking, but I'm just offering one approach, to this manipulation. So high is the phase that is most salient on both properties. Eyes are most distinct from the other members of the process faster, and the lips are the most distinct when compared to the other members of their process faster too. But unlike this guy, which is because of the proximity to these 2 opponent members, face members, both features are kind of slowed down, and that's how we get this factorial design. Now, so here's a Sabave interaction conscious function, right? So we have to find somehow a way from here to here. Yeah, how do we do that? Now you just make this experiment. You isolate these 4 conditions, and you repeat this task, many times with these faces, and you collect 4 different reaction time distributions. So these are density functions. Frequency as a function for the reaction time pins. So reaction time distributions, and everybody's familiar with that. High, low, high, and doesn't tell much. It looks pretty much identical here. So what we do, the next step is we have to turn this into survivor functions. And so another step is also relatively simple if you're using SPSS or maybe some other statistical software. What you have to do is you have to press one button, and then this button will calculate first cumulative value for the numbers of trials for this reaction time distribution, and then we'll take the inverse of that, 1 minus that function, and we'll return, this Sabave function. So it's everything, just a couple of clicks away. So there's not much to do. You don't even have to know what is the property of a Sabave function in order to generate this kind of experiment. You only need to have design. You have to calculate. You have to collect reaction times, and then we'll find a way to find the estimate, empirical Sabave functions. Now I have this symbols here, ugly, but just ignore them and that. So do this for 4 times, yeah, and we see that each Sabave function are corresponding to observed data are aligned with respect, to the particular expression here. Sabave function for this condition, Sabave function for low, low, that's it. Sabave function for high, high, this is the Sabave function. And we have to find the double difference between these 4 functions. plug in appropriate symbols here, minus, minus, plus, and the resulting function, boom, it looks like this. Now, what is this function? It's negative pretty much all the time. And if we go back to the catalog, we can identify it as a parallel exhaust process. So that's one way to do it. Do you have any questions so far? Please, ask questions, or should I step back? Or I mean, this is an important step. I just wanted to show how this is relatively simple. It's not a booky or doesn't really require much mathematical understanding how this exact calculation works. Now, I'll just show you one case, two cases where we apply the SFP in the case where we have continuous stimulus dimension, where saliency is actually lying in a continuous dimension. And we take this configurable second order facial features, eye separation, nose position, and we show in these two cases conjunctive rule stimulus structure, so-called OR and AND designs. So here it is. It looks maybe abstract, but we are not far away from the previous graph. Notice, that I repositioned these four members here. Then when you compare to the previous graph, but you can do whatever you wish, as long because you're the creator of the research design. In this particular one, these four guys will make this factorial design, and they pick up some values here on the eye separation dimension, which is kind of continuous value. Right here we have ellipse position, another continuous dimension of a facial property, and you decide, okay, these guys, for example, let's fit him against another guy we call hero, right? And so we have four guys here and one guy here, and this is a gang, and this is a hero. Your task is to, when one face is presented at a time, to say, do you see a gang or you see hero? Is it difficult to ask this one? Probably not. In order to learn whether, for example, when that face is presented, you can use two different rules. You can use two different rules to classify that face here, hero. Yeah? You can use this value on the eye separation as a criterion for decision making. It says, oh, look, I see the face, and the eye separation has value E3, and that's from the right-hand side of the decision criteria, that must be hero. So you don't have to pay attention to ellipse position at all. Likewise, you can do the same thing, for the other dimension, if you consider the first. This is the case when we process information in sequence. If you process information in parallel, first dimension that finishes will trigger the response. So this is why we said this approach, this OR stimulus, this disjunctive category stimulus structure is analytic friendly. It goes well with analytic type of processing. You don't have to process everything. You can just process one phase dimension and you can arrive to the solution. All right, this is OR design. And you have to analyze only 4 cases, and analysis of 4 cases and calculating the value function will tell you what happened really. We could expect, to see some analytic methods. Now here's another design. It's fairly similar to this one, except the position of the other group members are different. Now we have 2 guys here and 2 guys here. As you can see, these guys and these guys share properties with the target category on that dimension and on this dimension. So you can already imagine that this is a much more difficult task. And why is it difficult? Because you cannot use a single rule to make a decision here. So let's say this face is presented here, the JETS member, this one, and then if you take a look and let's say, oh, let's pay attention to eye separation. Oh, eye separation has value of 3, let's say maybe maximum, and probably you could say, oh, look, this is a JETS, So it's, in this case, this is a very fast decision. But if you somehow first pay attention to the ellipse position and read, this information, pay attention to that face, you say, oh, look, this could be any of these 3 faces that I met before. So I don't know which one it is. I have to pay attention to eye separation. So in some cases, you have to conduct exhaustive processing. You have to analyze both dimensions. So this is what we call this is holistic friendly. Holistic friendly, I put quotations here because it's not really implying any holism, but you have to process all information in several cases. In matter of fact, in order to categorize target shock members, you always have to process all information, because each of the shark members shares feature with the jets. Jets could be categorized, classified based on one property, but these guys have to be consulted in both dimensions. Otherwise, you cannot make a good decision. And that's called AND gate, because it refers to the target part. All right, so I show you this disjunctive and conjunctive stimulus rule categories. They probably give rise to analytic processes here or holistic processes. We don't know what kind of processes actually we're going to see there. So